Hello, today using this what looks very complicated at the moment device, we are going to measure the speed of light. What we're going to do is I have this hooked up to an oscilloscope in two different spots, this reference and the delay. What happens is this is going to put out a pulse of light. If I turn this, you can see it looks like a nice constant red light. It's not actually constant, it's pulsing very fast. And what we're going to do is here, we're going to record the light being made and when the pulse happens. And in the output, we're going to record when the pulse comes back in this black knob. Basically, we're going to send the light out here and into there. Now, before I explain how that's going to help us measure the speed of light, let's go look at our oscilloscope. Right now, we have our volt size set to 0.5 volts per centimeter, that being our y-axis, and our x-axis is 0.2 microseconds per centimeter. That means each of these squares is 0.2 microseconds or 200 nanoseconds. Now, if I set this to input, this is our pulse. That pulse, as you can tell, is really fast, being that this centimeter thing is 0.2 microseconds and it's half that. Now, that's actually as small as this guy gets for the size of the steps. However, there is a magnification knob. When I pull this, that is going to do a 5 times magnification. What that means is each square is 0.04 microseconds or 40 nanoseconds. And that means we can look at this peak, which I'm going to move around to try to center a little bit. Now, once again, just looking at the size of this, keep in mind that square is 40 nanoseconds. So it's a fast little peak. Now, what we're going to do is we are going to go and we are going to have the light travel through a very, very short and also misplaced piece of fiber optic cable. The fiber optic cable, what's going to happen is I'm going to hook it up so that it comes out here and into there. So I'm going to set that up real fast. And now with it hooked up, it's just this tiny little thing going through. It's only 15 centimeters long, which when we talk about the speed of light is basically nothing. I'm now going to compare this, where this is the peak with the light being made, to the light that's coming in by putting both channel A and B on at once. Now, it doesn't really show much at the moment. I think it's really tight. I'm going to see if I can get this on here. Oh, there we go. So there's our little peak. As I said, much, much shorter. So with our little peak here, I'll probably just jumped a tiny bit. What I'm going to do is I'm going to make it so I see both things. And on the speed of time thing, there's a knob. That's going to allow me to line up in 0. And what I'll do is I'll mess with the heights so that the two peaks line up. And I'm going to make it so the peaks happen at the exact same moment. Right about there. That's just to calibrate. Now that it's calibrated, I'm going to remove my tiny, tiny fiber optic cable, which is going to make that disappear. And I'm going to attach a big one, this huge coil. This thing is 20 meters long. And it's just long enough that there should be a noticeable difference in the amount of time it takes the light to pass through. So I'm going to put it in. And what you can see is the peak is now in a different spot. So what I'm going to do is I'm going to measure the distance between the peaks, remembering that each peak is 40 nanoseconds. And so let's put that right centered. There's my peak. As you can see, my peak happens in 1, 2, I'd go as far as say 2.5 squares. So we'll say that it's 2.5 squares oval, or a shift of 2.5 centimeters. And from there, we can try to calculate everything. It's a little quick, should be pretty doable.